Hello, everyone, and welcome to today's e-showcase, Value of Single-Source Providers of Emerging Contaminant Removal, including per and polyfluoroalkyl substances. I'd like to thank today's sponsor, AVOCA, sponsoring today's event. Today's presenters are Jeff Palacia, Business Development Manager for AVOCA Water Technologies, and John Lombardo, Senior Product Manager, AVOCA Water Technologies. And now I hand the presentation to our presenters.
Good afternoon, everybody. My name is Jeff Palacia, and thank you for joining us today for our webinar on the value of single-source providers of emerging contaminant removal, including polyfluoroalkyl substances, or PFAS. Many of you know PFAS are a problem in our community, and maybe that's why you have joined us today. We are excited to put on the webinar to help you further understand water treatment for emerging contaminants. For the outline today, this is what we plan to cover. I will cover the beginning overview today and end with the wrap up. And John Lombardo will cover solutions and present some case studies. We'll save time at the end of the webinar to take questions. And now with that, a little bit of intro on AVOCA. And I would just say, in a perfect world, there would be no emerging contaminants. Unfortunately, we now have PFAS. So we are going to talk about how we're handling that, how we're treating that, and how we're a single source provider for that. So a bit about AVOCA. AVOCA Water Technologies is a leading provider of water and wastewater treatment solution. We offer a broad portfolio of products, services, and expertise to support industrial, municipal, and even recreational customers. We offer emergency, mobile, and permanent water treatment solutions across our group. And within these sectors, we employ one of the largest and most diverse mobile fleets in the country. As you know, water plays an instrumental role in so many aspects of our daily life beyond drinking water. AVOCA can provide solutions for customers with critical water needs across the key market sectors that are shown on this slide, like energy generation, wastewater, oil and gas, manufacturing, and many more. Today, we have 160 locations and over 200,000 installations worldwide. So what's the current status of environmental compliance regulation? You may have seen the new EPA roadmap that came out on October 15th, and I'll get to that in a minute. But for water, currently EPA is being pressured to finalize regulation and evaluate lifetime health advisories through their PFAS action plan. There are emerging EPA standards for wastewater with PFAS, but again, these are just guidelines. So in the absence of the EPA regulations, local states have taken the lead on setting their own state-by-state action levels. And what we found in some cases, they're even more stringent than the current federal interim guidelines. The current interim guidelines came out in 2020 using the Drinking Water EPA Lifetime Health Advisory for just the two compounds, PFOA and PFOS at 70 PPT, combined or individual. And lastly, there's just limited data of known and detectable PFAS, including precursors, replacement compounds within the influent wastewater, as well as a need for improved analytical test methods that can even detect these compounds. So we would expect, and you can see on the next slide, early 2022 by the EPA, I'm sorry, that slide didn't get in there, but I can just run through that really quick. So the EPA's roadmap is they want to establish a national primary drinking water regulation for PFOA and PFOS, and they're proposing that in the fall of 2022. There's several other things on there. They want to publish health advisories for Gen X and PFBS in the spring of 2022. And also develop some better test methods for detecting the PFAS compounds, like I just mentioned, some of these oddballs, the precursors, the short chain, things like that. For your reference, a full report is available at www.epa.gov/PFAS. We can put that up in the chat later. So let's get into sources, routes of exposure, health effects. So for sources, I think the picture tells a story. Contaminants enter the environment through various sources and eventually make their way into the soils, the groundwater, the drinking water, and eventually us, humans. Some examples are chemical manufacturers or producers of these compounds, some commercial applications that are used in industry, landfills, wastewater effluent, and even firefighting foam application for fighting fires. All of these can contribute through exposure routes like occupational exposure, the drinking water, atmospheric transport to contaminated food products, which over time can contribute to adverse health effects. One of the largest studies conducted for PFAS was the C8 health study in 2005 to 2006. This study looked at human blood serum and was performed on a population of about 70,000 people who were affected by contaminated drinking water that had PFOA, or better known as C8. The study focused on 6 water districts across 2 states. And what came out of that is the results showed elevated levels of PFOA in the population, and we have since learned these high levels in our blood can cause several medical conditions. According to the CDC lab results from this study, they've linked it to adverse health effects to growth, development, reproduction, and even liver injury. So now I'm going to pass it over to John Lombardo, and he's going to discuss solutions and then show some case studies.
Thank you, Jeff. My name is John Lombardo. I'll be covering, as Jeff said, some solutions and case studies on PFAS as we go forward. So as you see now, there are different methods for removal solutions, right? So there's basically classifications of separation, which would be our granular activated carbon or granular activated carbon in general, and ion exchange, which separates the PFAS from the water. The membranes are they're capture. They actually capture it and adsorb it. Membranes are separation, which physically separates it. So in the case of membranes, you get basically an effluent stream or a permeate stream and a concentrate stream. The permeate stream is contaminant free for the most part, or is much lower in contaminant concentrations. And the concentrate stream is actually highly concentrated now with those contaminants. That's the separation piece of it. Carbon and ion exchange are basically adsorption or capture. They both work on the adsorption principle. Granular activated carbon is named best available technology by EPA for organic contaminant removal. It does remove other organic contaminants as well as PFAS, so it's very good at removing halogenated compounds from water, PCE, TCE. It's good at removing other things, sort of maybe from gasoline that's gotten spilled in the soil as well. It's a very minimal maintenance operation. There's not a lot of moving parts. It's just a flow through, pump and treat, if you will. Single pass ion exchange uses a resin bead, a plastic resin bead, to accomplish the same thing. It's actually a combination of adsorption and exchange. It runs at a lower empty bed contact time, that's EBCT, runs at a lower empty bed contact time than granular activated carbon. For carbon, the industry standard is about 10 minutes of empty bed contact time. For ion exchange resin, it's typically in the 2 to 3 minute range. So you can run it at a higher flow rate, and usually it requires a smaller footprint because you have less volume of resin. There's no chemicals for the single pass or liquid waste, so it's kind of a once-through system, and the spent resin can be sent off for incineration. It also requires minimal maintenance because it's a pump and treat type system, so not a lot of moving parts and no regeneration. So how does granular activated carbon work, or why does granular activated carbon work? Granular activated carbon is really a very highly porous media which has a tremendous surface area. About 1 teaspoonful has enough flat surface area to cover a football field if you could kind of spread it out. So remember, that's just a flat surface. There's really no depth measurement in there, but on a square footage. So it's an extremely porous and highly surface covered area. And in the diagram you can see on the top right, which is kind of a depiction of a granular activated carbon grain, there are basically 3 types of pores that are covered in there. There are macropores, which are the largest pores. And then there are mesopores, which are the medium pores. And then there are micropores, which are the smallest pores. Well, adsorption takes place in the micropore zone of the carbon. So the contaminants that you can see there in the green and the other, I'll say purpley red ones that are in there, they work their way through the structure of the carbon, through the macroporous structure of the carbon, then transport using the mesopores down to the micropores. So the contaminants are then stored in the micropore section of the carbon. So all carbon is not created equal. So one carbon, and it all depends upon really the raw material and the activation process. So the performance there is determined by the porosity and what we call the surface chemistry. The best thing is to know that on an individual water source, you are matching the best type of carbon for that particular solution. Some carbons are more microporous, some carbons are more meso or macroporous. So knowing what is in your water really is the best way to determine the best type of carbon. So there's really not a one-size-fits-all approach in this type of operation. So how does ion exchange work? So ion exchange is in essence a plastic resin bead, and it's based on the principle of exchanging a harmless ion for the contaminant. So if anybody is familiar with softeners for home or other types of things like that, where you're exchanging calcium and maybe magnesium for sodium, that's the same type of principle, but it also works on an adsorption. So after the contaminant, so kind of the green globules that are there in the diagram, are exchanged on the surface of the ion exchange, it absorbs into the structure. And in this process, we're exchanging chloride as the ion exchange for the contaminant. It requires a smaller footprint, so if space is an issue, ion exchange may be a more attractive option. The life cycle costs are a little bit easier to predict, whereas carbon is a grain, really. It has a kind of a very rough look to it. The resin beads are usually, in this case, the ones that we use are relatively uniform in particle size, so pretty easy to predict absorption and different things. And the spent resin, once exhausted, can be sent off for incineration. So how do you determine what is the better option? That is done through performance testing. So there's typically 2 types of performance tests that can be run. The first is a pilot, which is the drawing shown on the right, and then the other one is bench scale testing. Pilot testing is usually done at the site, and it's run on a slipstream of the influent water that's to be treated. And it usually runs for a length of time anywhere commensurate to 6 to 12 months of operation. So what you do is you would replicate a full-scale system on a much smaller scale. So you'd have probably the ones you see here are 2-inch diameter columns. So you would fill the bed depth and match the hydraulic loading rate and empty bed contact time to what you would design on your full flow system as a smaller scale, and then you would operate it. So pilots usually run, like I said, 6 to 12 months in duration. And they're a good measure because it takes into account seasonality, fluctuations, different types of things that go on during the thing. So if you have a surface water, which is prone to turnover, whether it be lake water, pond water, any type of surface stream or river that you're drawing from a source, piloting is a good way to basically take into account seasonality. So, as leaves fall, if you're in a part of the country in the northern part, that leaves fall into the water, and then other things, you have animals, you have runoff, you have a whole bunch of other things, rain that collects in there. It might be a better option for you. However, the time may be, unfortunately, in a lot of cases, there may be some quick constraints on this. So you may need to go with what's called an accelerated bench scale, or a rapid small-scale column test, RSSCT abbreviated, which can simulate months of runtime data in a matter of days or weeks. So instead of running a pilot for 6 to 12 months, an RSSCT test can be run in a matter of 2, maybe 3, maybe as many as 6 weeks, depending upon the contaminant and the concentration. The one disadvantage on the RSSCT is that it's a snapshot in time. So you're taking a sample, usually like a drum of water. So you're taking, 55 gallons sample of water and using that as your basis. Now, if you have a groundwater source that's pretty stable, then it's a pretty safe assumption. So there are pros and cons on each one, length of time, testing, cost, availability, other things. So this all goes into the factor of what's going to be the best measure for me or for my municipality, utility, source, whoever the user is, to determine what's the best way to benchmark their performance and what they would expect in a full-scale system. So we also have mobile units, so that if there's something that happens when there's when your process can't be interrupted, or if there's an event-based driven thing where you've run into, in this case, as you see in the picture on the right, this is part of a construction site. So when you dig into the ground and you hit water from the water table, that water needs to be treated for discharge, whether it goes to a POTW or back into the ground for replenishment or to a surface supply. So AVOCA has emergency rapid response equipment for on a temporary or semi-permanent basis that can be mobilized to a site to treat that water and make sure that it's clean enough for discharge back to the environment or to the POTW. We have flow rates from 50 to 2,000 or more GPM. It can be done for industrial process water and industrial wastewater as well. There's variable footprints based on size and constraints, and some of the equipment may be skid mounted or trailer mounted to fit and make it easier for you to operate on your site. Now I'm going to cover some case studies. The first case study that I'm going to cover is actually from a lakefront development in Western Michigan, where they were doing, once again, construction, and when they hit the water and tested it, they found that the water inside that construction area was contaminated with PFAS and metals and other things. So in order to basically treat that, AVOCA mobilized some trailer equipment and some frac tanks and other things to go on the fly treatment. So it was kind of a real pump and treat. They were taking the water out, treating it for metals removal, and then treating it for PFAS removal, and then discharging. The city, in this case, set the treatment goal to non-detect. So that meant that they wanted the effluent in the PFAS to meet the current detection limits of the analytical, which right now is about 2 ppt or less. In this particular instance, the treatment goal was met throughout the entire project, which lasted about 6 months during the construction cycle. So it was a very simple, but yet very effective solution. This is another site around the corner, same type of thing where they were doing some digging for construction on a highway, and the water tested positive for PFAS, and they had metals and other organics in there that needed to be treated. What they decided to do was drill a wellhead in there to pump it out. And as they did that, they mitigated for PFAS, arsenic, mercury, and other. And in this case, the cleaned effluent or the treated effluent was discharged into a municipal sewer. So all sorts of solutions. You can see some of the equipment back on the right, multiple tanks, frac tanks, other things that are there that can be used in a combination to be able to treat effectively and discharge water within compliance to the local standards. This is a temporary system that was installed in Colorado. It was an emergency solution to mitigate some seasonal taste and odor issues for a municipality. They were struggling with some MIB and Josmin, methyl isoborneol, and Josmin issues in their water, imparting taste and odor. And the municipality had plans to put a new treatment facility in, but it would be years in the making between the design, the implementation, the permits, the funding, the whole 9 yards. But they needed a solution before the warmer weather came and tourists and others started arriving on the scene. AVOCA ran an RSSCT, rapid small-scale column test, on the water to determine that the right GAC was used and that it would remove the MIB and Josmin to acceptable levels and treat for a certain length of time, so that they could use this system temporarily during the summer so that they could then continue on with operations. Another one is Kennebunk and Wells Water District in Maine. Years ago, they just had developed a new well, and when they were doing the well testing as part of the UCMR3 rule back in 2016, they discovered PFAS in the well. Excuse me. So they piloted several types of carbon to determine which one performed best based on their local water chemistry. In this case, results showed that AVOCA's carbon from coconut shells, or enhanced coconut shell, provide an additional 3 months of full-scale runtime versus other carbons. And on the next slide, I have a little graph there that will show you just how everything kind of played out. The municipality installed a full-scale, high-pressure vessel system to treat for the PFAS based on the results of the pilot. And you can see in the picture on the right, if the screen is caught up, that's an actual photo from the pilot that was run up at Kennebunk. And you can see the results below. You see the line up at the top at the 10 was the influent for PFOA. This is just one of the contaminants. And you can see that we ran some regular coconut, some bituminous coal, and then our enhanced, our CX, enhanced coconut carbon. We ran the virgin, which is the yellow line on the bottom, and then a react, which means it had gone back for reactivation and come back to be reused. And we ran, you could see that the react and the virgin outperform both the standard coconut and the coal. So they installed a permanent solution. They had a sand filter put up front, and they put a little bit of chlorine in it to remove iron. And then they used a lead lag operation with GAC. So it was, worker polisher or lead lag. They're 12-foot diameter vessels. They are 20,000 pound adsorbers. So that was the volume. But because of the lower density of our CX media, they only filled both of them with 34,700 pounds. It met we designed it for the 10-minute empty bed contact time, but because of seasonal operation, they were running closer to 8. It was originally an outdoor installation, and they did what we called custom segregated municipal react and return. So they had this carbon, they'd send it back to us in our NSF 61 kiln and our Darlington facility. We would reactivate the carbon, make up with fresh virgin carbon, and send it back to them for further use. The system incorporates what we call our SEPTA design, which is the picture in the lower right of that, which these are internals or bottom internals that stick up through the bottom of the tank. It allows for a lower profile design, and it allows for flexibility so that if they ever in the future want to go to an ion exchange resin, all they need to do is just swap out the top distributor and they can load the resin in, and there won't be any change to the internals at the bottom. It's actually a very unique design. And it allows for greater flexibility in operation. The goal of the municipality was to get the system online in time for the tourist season, and they basically said that they have had no problem with it. And the overall impact to the ratepayers was 3 to 4 cents a day, and that'll take years to come in until after they get everything settled. And it kept them independent. It was cheaper than buying water from another municipality close by, and allowed them to continue their operations and kind of control their own destiny. Another case study, this is in the Southeast United States. It was a groundwater with high TOC. It had been under influence from PFOA and PFOS. They were really unsure of the source of the contamination. The concentrations were above the LHA, the Lifetime Health Advisory, the EPA Lifetime Health Advisory Jeff had discussed earlier. The opportunity was brought to AVOCA through an engineering firm. I said the water had high TOC, it was about 14 ppm. Their treatment objective was to get PFOA and PFOS under 10 ppt. The pilot, which you can see over on the right, was done on both carbon, GAC, and ion exchange resin. So the initial results were putting carbon first, and the carbon, because of the high TOC, fouled within 3 days and had to switch over to ion exchange resin. So once the ion exchange resin was put into operation, the resin turned black within 24 hours, but yet it still provided sufficient removal and no pluggage. It operated superior to the carbon in this case. The engineer in the municipality decided to move to a full-scale comparison with ion exchange from several different manufacturers. And you can see the results down there. And AVOCA chose a Dowex PSR2 Plus as the resin. And you can see how the performance was on several of the long and short chain contaminants. In the full-scale study, they used 4 different resins. The vessels had the SEPTA design that we covered in an earlier slide to provide greater flexibility for operation. In this case, PSR2 Plus seemed to provide the longest throughput on this, so the customer ended up rebedding with PSR2 Plus going forward. Basically treated a greater volume of water before exhaustion. I'll turn it back over to Jeff for the wrap-up.
Thanks, John. And I think we just learned the value of a single source provider of emerging contaminants. We offer unbiased technology in a portfolio of comprehensive solutions from start to finish. So with that, we're technology agnostic. We are solution providers and try to design the system that best fits your needs. We can rapidly deploy mobile assets to your facility, for example. We can offer treatability studies to help identify the best available technology that's out there today. We can offer the permanent on-site solutions, which you saw in some of these case studies as well, and employ a dynamic servicing network able to be on site in most of the US within 2 hours. And our reactivation services to help regenerate the carbon. And again, finally, our knowledge of disposal options to help you see the end. So it's really start to finish here. So what are the next steps? The next steps would be, let's assess the risk, determine the regulatory requirements, understand any public concerns and brand protection, obtain some background water quality and PFAS analysis. The water chemistry is very critical to when we're designing a system. So we really need to understand what we have coming in and what we need to treat to. Determine if there's any remedial alternatives. So understand the life cycle costs of the system. We can look at if there are any destructive technologies that are available and what are the disposal options. And lastly, decide what type of upfront site-specific testing methodologies, whether it's a pilot or an RSSCT, as John went over earlier in the case studies and the examples. So in closing, your water is unique, and we can determine a customized solution just for your community based on the local water conditions. And now it's time for some questions.
All right, great. This was excellent. So we do have one question that has come through right now. If you would, please go ahead and take this opportunity to chat your great questions or comments about the presentation to the everyone or all panelist option. But for now, we're going to go ahead and start out with a question to John. What is the minimum time required to do an adequate pilot test for an 800 GPM groundwater system?
Excellent. Thank you. Thank you, Regina. That's a great question. So for a rapid small-scale column test, it would take about, 4 to 6 weeks, depending upon the concentrations. For a pilot with either carbon or resin, it would probably take about 1 year.
1 year, great. And then there's another one for you, John, as well. How does GAC perform for removing shorter chain PFAS, PFAS?
Excellent. Thanks, Regina. So in general, carbon does not absorb short chain PFAS as well as IX resin. Not to say that it doesn't work. It still absorbs it pretty well. It just doesn't have the capacity or as much capacity or longevity as ion exchange resin. Both carbon and resin have background water interferences, so things that will compete. So aligning overall treatment goals with your testing, whether it be bench or pilot scale, is going to determine the best media solution. So it doesn't always mean that if you have more short chains, ion exchange resin is going to be a better solution. It may be, but it depends on other things, other factors in there. So what other competing anions, maybe like chlorides or sulfates or other things that are in there that may be competing for those same sites on the ion exchange resin. So it's more of a guided approach. You can use it as an indicator, which may be a better one. And in some cases, there may be tandem approaches where you start with carbon and maybe polish with resin, if it depending upon, like I said, what your overall treatment goals are and what's going to be, economical, most economical and effective for your solution.
And I believe this may be a follow-up to that question. Is any of the GAC able to be regenerated?
Thank you, Regina. So yes, so carbon can be reactivated. I'll say a nuance in terminology. Yes, so carbon can be thermally reactivated and reused. In municipal applications, as we talked about in the Kennebunk, case study, the Kennebunk case study, they were actually taking their carbon and then sending it back to us. We would reactivate it and send it back to them. The reactivation process drives off the volatile organics and kind of cleans up the carbon and gets it ready for use. And then there's some attritional losses between transportation and handling and other things. So any of those attritional losses are made up with virgin carbon and given back to the customer. So the customer gets back their specific carbon with fresh virgin carbon used to kind of top off, if you will. So yes, and carbon can be reactivated, at least in municipal cases. In certain other things, maybe industrial where the concentrations are higher, it needs to be evaluated. But for most municipal applications, yes, reactivation is a very likely scenario. And it's a very cost-effective, can be a very cost-effective option to providing new virgin carbon every single time.
Okay, great. I've got one question here. I'm not sure if Jeff or John can respond to it, but what about desorption of PFCs from the GAC IX to water?
Desorption of PFAS on ion exchange resin? I think do you mind repeating the question?
Yeah, it just says, what about desorption of PFAS from GAC IX to water?
So usually once it is bound, it stays on. Now there's such a phenomenon as called bed rollover, right? It's like a chromatographic effect, and it's typical of any adsorptive media, whether it be carbon and or resin. So in other words, if you're bombarding something with a much higher concentration of contaminant, there's certain selective preferences that the media will go for, right? So something that's more highly selective, like longer chains versus shorter chains. If there's opportunities where you're overrunning it with higher concentrations, once you've gone through the mass transfer zone, you can actually displace it. That's why we usually recommend against backwashing either a carbon or a resin system after it's been in operation, because you don't want to disturb that mass transfer zone where the exchange and the adsorption process is taking place. That way, because if you're putting pure water on top of contaminated water, you might start to get some leakage. So typically it doesn't happen if the system is operated properly. And of course, if it's been designed properly from the beginning, then it usually does not happen. But there is a possibility in some cases where you'll see preferential absorption take place. So you may see an increase in concentration of one over the other. But like I said, if a system is designed and operated properly, that really should not happen.
All right, great. And then I think this one is maybe directed to Jeff. Do resin and carbon systems utilize the same type of pressure vessels? More specifically, can a GAC vessel be easily converted for use with resin?
That's a good question, Regina. So yes, a GAC vessel can be converted to an ion exchange resin vessel. The inlet distributor and outlet screens must be selected, though, and appropriately based on the size of the resin that's being used.
All right, and I think here's one more for you. What about in situ treatment options for PFAS?
Another good one. So didn't really touch on this, but with PFAS, it's the carbon fluorine bond. So the chemical makeup is one of the strongest in chemistry and very hard to break down. The issue with in situ treatment methods such as an oxidative process is that it would require a large amount of energy to really break these bonds and ensure that these compounds were completely destroyed and not forming other daughter products, almost like transforming.
All right, great. And we've got more questions here. What is the largest plant gallons treated with either the ion exchange or GAC used at?
This is John Lombardo. I don't know the specific answer, but that, you know, the largest one that's operating, whether we've sold it or a competitor of ours has sold it. You know, our experience is we have systems running in, you know, 4 to 6 MGD operation that are using for treatment of PFAS, either carbon or resin. We have operations for both. We know larger ones are on the horizon. Orange County Water District in California, out in Los Angeles County, has undertaken a very, very large study. And I'm not sure what the overall thing was, but I'm going to guess that that's probably in the tens of MGDs that they'll be looking at. And they're already in the process of procuring and getting ready to run full-scale systems. In their case, they're using, because of the water quality and all the other things that are going on there with the groundwater, they're actually going with ion exchange resin as probably the primary, and then they have some other options in there as well. But right now, I mean, the largest ones that we're involved with are probably, I'm going to say, in the 4 to 6 MGD. Beyond that, there are certain things going on, but we, you know, there may be other ones that are larger, but right now, I know that you know, I'll say our sweet spot's probably a little smaller, but we've done systems as large as 4 to 6 MGD in capacity, and it's never been a problem. So I hope that answers the question. If not, just, you know, send me an email or whatever else we can follow up on.
All right, and their email addresses are on the slides to your left, and I will put them in the chat in just a moment. So we've got another question here. Do you use RONF membranes to remove all the PFCs?
This is John Lombardo. Good question. Yes, so RO and NF can be used to remove or separate PFC or PFAS. So yes, the issue is that it separates them from the permeate and puts them into the concentrate. So now you have a smaller, and that smaller flow could be anywhere from 25, you know, 10% to 25%, depending upon the recovery of a stream. So for every, in this case, so for every 1 gallon of water you're treating, you're going to get anywhere from 0.75 to 0.9 gallons of effluent or of treated water, and you're going to have a concentrate stream of a quarter gallon a minute down to a tenth of a gallon, I'm sorry, a quarter of a gallon down to a tenth of a gallon that has to go off for either further treatment or storage or disposal or whatever. Right now, the membrane process, the separation really is being viewed as more of a concentration step so that people can concentrate that and then put it in for further treatment. But really the issues with the membranes is it's a very labor and footprint intensive solution. There are some cases we know of 2, one in North Carolina and one in Alabama, that are being used for treatment. But in both those cases, it's because the influent water wasn't just contaminated with PFAS. There are other contaminants in there, 1,4-dioxane, pesticides, pharmaceutical byproducts. So the RO was actually best at cleaning them all out of the water. However, they're just having to deal with the concentrate stream now on a separate. So as opposed to having multiple technologies pumped in, what they're doing is just using RO to separate it and kind of deal with it separately.
All right, great. So have you used PFOS treatment system in reclaimed wastewater? And there's a second question to that. What are the major constraints to use these treatment processes in reclaimed wastewater?
This is John Lombardo. I'll take that one. Great question. So in reclaimed wastewater, the issue is treating the competing organics, whether it be for the carbon or the resin. There's certain organics that will, even though, you know, we had shown in the Southwest United States case study that 14 ppm of TOC really didn't affect the resin much and perform well. In wastewater applications, those numbers, particularly like when you go to the BOD and COD, usually are in the hundreds. And there are certain concerns. So Typically, in those cases, you'd be looking to do kind of a pre-treatment step on that, whether it be a biological or some type of oxidative technology to kind of break down those TOCs so that the carbon and resin will last longer. Otherwise, it's a very, very expensive proposition. The payback, the cost benefit of it is not there. The carbon and the resin would exhaust too quickly. So usually there's some type of pre-treatment required to kind of work down the organics and maybe even remove some of the other competing contaminants prior to treatment with carbon or resin.
All right, great. And I think this one is going to go to Jeff. What about in situ treatment options for PFAS? I think we may have already answered that question.
I think, yeah, hang on. I was just scrolling up. I think I did answer that one, but I can do it again if someone else said. Okay.
Yep, we did. We'll move on to another one. And actually, I've got one for John. What would you suggest between rapid test versus full-scale pilot?
Excellent question. This one comes up quite a bit. So for piloting, like I had mentioned, it's a more robust treatment. It takes into account seasonality. So if you have surface waters or waters that are subject to changing for any reason, whether it be season or other things, other factors, you might have surface water under the influence or groundwater under the influence of surface water, different things like that. Piloting may be your better option, even though it's longer. If you've got a pretty static water supply, like a groundwater that's not under the influence of a surface water, that's pretty stable, lower TOC, kind of checks a lot of the boxes, a rapid small scale column test is probably going to be your better bet. Now, it's not to say that those are guidelines. Those aren't really hard and fast rules. There's cases where one will be preferential over the other, but by looking at the overall water chemistry and looking at the seasonality of it, so looking at an water analysis over the course of a year, 18 months, and seeing what goes on with it, really is the best way to determine what is going to be your more effective. Now, of course, there's other factors, budget, timeline, labor availability, right? Because pilots have to be operated, and PFAS testing is not inexpensive. So, pilots usually cost, I'm going to say maybe 3 to 6 times as much as an RSSCT, just because of the duration and the testing, which can be very expensive. I mean, it can be as much as 10 times or more, but it's usually a far more expensive proposition. And where I said it does take time and there's labor constraints, and if it's outdoors and you're up north, then what do you do? So I said there's a lot of factors that kind of go into it. It's more of a guideline than anything else. So, but looking holistically at what your influent and what your effluent is really the guiding principle for whether you should go with a pilot or an RSSCT.
All right, great. And I've got one for Jeff. What is the typical process for these projects from discovery to installation?
That's a good one. That sounds like a good follow-up to what John just said. So from discovery, I would say after you've got confirmed detections of PFAS by a utility or site, it really starts with the engagement their engineer, whether it's an in-house or external, and try to come up with, what's the current situation. In many cases, speed is an important consideration when choosing a solution. So the solution usually depends on each customer's specific needs, as we've mentioned here in several of the different studies. And because each site is different, we recommend a pilot and or bench scale performance test. So these tests, along with the customer criteria of budget, timing, and treatment goals, will help determine the correct media and system. So I hope I answered that.
All right, and if that question was not answered, you can put in a follow-up question just so that we can clarify. But we've got one more question here. How do the costs compare between carbon and resin? Maybe for John, you might be able to tackle that one for us.
Virginia, that's another great question.
Yeah.
So resin is typically 3 to 5 times as expensive as carbon, but when you're considering the empty bed contact time for resin is 3 to 5 times less, right? 2 to 3 minutes versus 10. The run times or run lengths between the media tend to be comparable because while you may have you know, a smaller amount of resin, right, because of the empty bed contact time, you've got a much larger volume of carbon to treat it. So the run times, while the bed volumes for resin will be higher, the throughput in gallons will tend to be comparable. The PFAS composition of the influent, along with, once again, not to kind of beat these things to death, but basically looking at the influent and aligning that with your treatment goals and then testing is really going to determine what's going to be the best CapEx and OpEx solution. And you know, each owner is different, whether it be a utility or an industry or whoever it is, whether it be, you know, the military or whoever you're treating for this. Some people have different goals for CapEx versus OpEx, and some people have different budgets for CapEx versus OpEx. So that's why using this kind of holistic approach, solutions approach, and looking at what, you know, what's going to be the best. So I said, it's never really a one size fit all. Even within the same community, we know of cases within certain communities where in one case carbon, you know, it's the town has two wells, and in one well carbon worked better, and on the other well resin worked better. And it's basically comes down to what's in the water, what's available, right? What are the treatment goals for each one, even though they kind of have the same ones, but by just even small changes in source water composition can have, I'll say, ripple effects on the overall design of the system. So it's not uncommon, you know, to see where carbon may work very well in one town, but the town the next over, which may be drawing off the same water supply, or even within the same town, but drawing off a different well, may have a different solution. So that's why we really recommend a more holistic approach in looking at the influent, what you're looking for effluent, and then a regimen of testing.
All right, this was great. That will actually end our Q&A for today. This was fantastic, Jeff and John. You have done a wonderful job. We are actually going to go ahead and close out today's e-showcase, and I just want to take this time to thank our presenters, Jeff and John, for presenting today, and I definitely want to thank our sponsor, AVOCA, for sponsoring today's event. This actually concludes today's e-showcase. Thank you all for attending. The recording will be available at wefbuyersguide.wef.org. We will send all registrants an email tomorrow with that link, and please visit our event calendar to sign up for future webcasts. Thank you all.
Thank you.
Thank you.